I think in the past lecture, in the previous lectures, we already covered how to calculate PDF for crystals, right? I think we have already done that. Yeah, we went through the whole process, and we also went through the fitting. I remember we took the titanium sulfide as an example, right? So actually we went through the fitting of the PDF for crystalline phase. So today we'll go through the PDF for the amorphous phase or small molecules, and probably that is more valuable or more unique than PDF for the crystals. Because crystals can be characterized in a lot of other ways, for example, through the diffraction. But how do we characterize the small molecules or amorphous phases? There are indeed other techniques like infrared or Raman or other spectroscopy, but still PDF has its own uniqueness, right? You can characterize the whole thing utilizing the high energy, and I think previously we have already found some good examples of using PDF to characterize the amorphous components in the interface. So maybe I can show a slide, right? Yeah. I think I should join the meeting, right, and then start sharing my screen. I think that's the way to go.
Yes.
Okay. So there are two meetings. I think should be there. So just give me a second. Yeah, so this one. It's my slides, right? Okay. So I think this is one example of how we use PDF to characterize the amorphous components in interface. We can look at the peaks A and B, right? So A is somewhere around 1.5 angstrom, and that is only from the amorphous components, something that is based on the carbon, based upon like carbon oxygen, carbon carbon, or the sulfur based, like sulfur carbon, sulfur fluorine, sulfur nitrogen, right? So A is kind of a unique indicator of the amorphous components in the base. And B is centering around 2 angstrom. So B is actually coming from the lithium-containing components. And our assumption is the lithium-containing components are mostly crystalline, right? It could be the oxides, lithium fluoride, lithium hydride, lithium hydroxide. They all start with the lithium oxygen bond, which centers around 2.0 angstrom. So a convenient way to differentiate their amorphous and crystalline components is actually just by visual inspection of the A and B peaks. And also, if we look at the A peak in detail, we see it's asymmetric, so actually it has some contribution from high R region, and also some contribution from the low R region. And the high region are mostly dominated by the sulfur-based bonds, which are longer. And the lower region are dominated by the carbon-based, which is to a lower R region. So yeah, this is the how we use in general use the PDF to analyze the interface components. But probably you wonder how we obtain this kind of a pattern, right? So you see this pattern here, and also this pattern for the for here. So this one is a pattern calculated for the model compound, and that model compound is based on the previous DFT calculation that people model their decomposition pathway of LIFSI. So this means they're fluorine detached from the FSI anion part. And since FSI is symmetric, so actually there's one fluorine lost from each side. So there's two fluorine lost, forming this kind of the fragment of the anion. And for the DME oligomer, it's also based on the previous modeling work that predicts that when DME decomposes, they actually form this kind of oligomer between the two DME fragments, producing the DME oligomer structure, and we can calculate that to obtain this kind of pattern. So today, what we're going to go through is how we do these kind of things, right? So if we suspect that there could be some amorphous components, and how do we do the PDF calculation for them? Okay, so that's the goal for today. And I have a slide here, so which is very simple. We need 3 steps. Step 1 is geometry optimization. Okay, we need to get an optimized geometry for the molecule, or for the point, or for the amorphous components that we expect to have, or we can check to see if it exists in the interface. The second thing is dummy structure making. So by dummy structure, what I mean is we need to create a crystal structure, right? And this is actually not a real crystal, but we need to create a crystal structure because we need to communicate with PDFGUI later. And for PDFGUI, it is very friendly to crystal structures. It doesn't really recognize the small molecules very well. So we need to, bridge this kind of a gap by making a dummy structure. What we need to do is we need to create a big unit cell, and then we put, this molecule in this cell. So that's basically a P1 cell, right? Each unit cell only contains one molecule. You can imagine, there are tons of Amazon boxes, big boxes, but there's only one atom in the center of that, right? So, and then through this way, we can trick the PDFGUI, telling him that, hey, this is a crystal structure, and please calculate PDF pattern for this, for us. So that's the whole, the logarithm, the algorithm, or the logic, how we do the PDF calculation for the small molecules. So for step 1, we need to do geometry optimization, and the tools we have actually are multiple. So I mentioned Avogadro 2 in the email, right? So that's something we can start with. In fact, I also mentioned WebMO. So that's an app. That's something actually I find convenient. So I think if you want to get the full version, you probably want to pay $4 or $5 for the full version, but it's quite worth it from my point of view. So, and WebML is something that you can do on an iPhone. That you can just draw a molecule and ask the software to optimize the structure for you, and then you can export the optimized structure to other software, for example, to Gaussian. Gaussian is actually a theoretical chemistry tool, right? So Gaussian can help us to calculate a lot of things, including optimized geometry of the molecule, and that depending on the how complicated the optimization is, but Gaussian can do very highly accurate geometry optimization, and that also gives a more reliable HOMO and LUMO, which we may be interested in later. But today we're just to talk about the Avogadro 2, which is free and very commonly used. It's used by many people. I guess the original Avogadro software has been cited several thousands of times, so it's very popular software. If you have already installed Avogadro 2, you may have something like this. So maybe I'll start from the beginning. Okay. So hope you have the same software interface as I do. So by the way, you also want to pay attention to the software version. So the one I'm using is 1.970. So you see the numbers here. So this is the version. Because Avogadro actually, they keep updating. So, I noticed that sometimes some of the version, may have some bugs that's not easy to work with. I have been using with this version for some time, and I find it very easy to use. It's user friendly. So, how many of you have already installed Avogadro? Can I see some reactions? Jane, have you installed already? No, not yet. Okay. Function have been, okay, you have one. One more, do you have? None, do you have that? You have that, right? Okay, so, but it's okay since the whole lecture is recorded. If you have not installed, you can install later and follow the video to go through the process, right? So now, if you have already have the software, you can start with me. Let's say we want to calculate the PDF for DME, right? So DME stands for dimethoxy dimethyloxyethane, right? So what I mean is that we have two methyl group on the end, and these two methyl group are connected to the ethyl group, right? And these two ethyl oxygen, they are connected by the ethyl group, two carbons, right? So we have one carbon, one ion on one end, and then we can switch to oxygen from the drop-down menu oxygen. And so we have oxygen here, and then we switch to carbon again. And we know that, from a basic chemical argument, they form this kind of a zigzag geometry, right? So that's plot the molecule in an educated way. We switch carbon. But then we just connect them. Okay, and in case we forgot something, especially we forgot some hydrogens, we can go to build hydrogen and just hydrogens. So this helps us to add some of the forgotten hydrogen, or just remove some of the surplus hydrogens. Okay. Now we have something like this, which makes chemical sense, but the bond lengths, they're kind of random. So let's go to extensions to optimize them, open Babel, and you see the optimized geometry. Okay, so let's click on that. So apparently it shrinks, right? So you know, reaches a more reasonable bond mass and bond angles. Before we go to the next step, we can stay here a little bit and we can, you know, explore some of the properties. So for example, we can measure the bond distance. Let's say we go to measure tools and we can measure just this carbon and oxygen. So you see the bond distance is 1.44, and this makes a lot of sense, right? So that's the expected their bond distance. Okay. So then we can save this molecule. We can choose the PDB form. We choose export molecule. And so I already saved one here, but I do it again. So let's just scroll down from the file types. And so you see Avogadro provides so many types of their format. Let's go to the protein database. Yeah, protein data bank form, PDB. So this is something that can be recognized by Vesta. Okay, so you see, you know, we are trying to do the whole thing from the cheap way. We do not have a paid or licensed software that really help us to do this calculation. There's some, you know, expensive software out there. For example, the so-called PDFGUI, which is Python-based, that was developed by Columbia University by Simon Lynch, but that cost several thousands of dollars. So what we're trying to do here, we try to integrate several free softwares, right? We put them together and ask them to do the job for us. And the challenge, or maybe the tricky part is, you know, we need to make sure the files, they communicate. I mean, the softwares, they communicate with each other, right? They should speak the same language. And the language is actually their file format. So we need to use the file format that is, you know, can be transferable among different softwares. Okay, so we can export from the Avogadro as a PDB. We'll just take one, just say the name. Yes. Okay, so now it's saved. Okay. And now then let's go to this one. Let's open Vesta. Again, Vesta is also free. Okay. So let's go to Vesta and open the PDB file we have just created. This one. So this one. So we see the molecule now in the Vesta version, right? So this is what DME looks like in Vesta. So you can still see the zigzag geometry and also, you know, the bond lengths, bond angles, they all seems to make sense. So for example, if we measure the bond angle here, so that's 114. I think that's makes general sense, you know, for this kind of zigzag carbon oxygen carbon bond, right? So now we are we'll go into step 2, which is to create the dummy structure. And that's the job of Vesta. In fact, that's the job of both Vesta and Mercury. I'll explain the reason a little bit later. So now we will ask Vesta to create a structure, a dummy structure for us, and to produce a zip file that will be regarded as a crystal structure file by PDFGUI. Okay, so we do that, you know, just to simply export data. ZIP, you see, I already chose zip files, right? So just want to make sure you choose the zip and you save as DME. I already saved it before, I just override it. Okay. And now we have the zip file. So as a matter of fact, when I was trying to go through everything by myself in the beginning, this is where I directly go to PDFGUI. So let's say PDFGUI. Okay. So I want to input that structure into PDFGUI, and I start a new fit. And on this new fit, I input insert face, and I load a structure from file, and then zip file, right? I just open the previous zip file. Go to the folder. So I have one zip file here. You see, this is, when the formality of the file matters. So even though it is a zip file, it's a crystal file, but it is not recognized by the PDFGUI because PDFGUI complains about the format. It's expecting a certain type of format for zip file. So that's why I suggest we also have Mercury installed, which is free. The free version basically provides enough capabilities that we will use. Mercury can also be very expensive, costing tens of thousands of dollars, but we do not need that. Right? So I think we already have J and Topaz, so I think we have already the full set of tools for the crystallography story. So we're not trying to purchase Mercury, but we can use the free version. So let's go to Mercury. Okay. So this is the free Mercury, how it looks like. And what we do here with Mercury is simply just ask Mercury to re-output the zip file, because I know that zip file is compatible with PDFGUI. Okay. So open. This is the original. And this is how DME looks like in the Mercury. It's still the same, right? We only see only one molecule here because by default it is only showing one unit cell. As I mentioned, there's only one molecule in one unit cell, so that's why we're only looking at one molecule. If you change the boundary setting, you'll see a translational symmetry of the DME. You see a lot of DMEs in parallel. So let's simply output this, save as, still zip file, but now we name it as DME Mercury. Okay. So to indicate this is a different format of the zip file, say yes. The zip yes. Okay, now let's say if the compatibility issue has been solved. Let's load, open, Mercury. Yeah, here we go. Yeah, this is one message, but it's complaining about the ADP, right? Hope you still remember what ADP stands for. ADP stands for their thermal vibration or disorder values, right? So it is called the B value in Topaz. It's also called UISO, in some other softwares like GSense, they will call it UISO. In Topaz, it's called B value. But in general, it's just ADP, which stands for Atomic Displacement Parameter, right? So that is indicating how the atoms are actually vibrating. So they're dynamically shifting from their ideal position, and also their statistic disorder from the ideal crystallography side, right? We did cover this in the previous lectures. So, if you want to have a refresh your memory about ADP for the previous lectures, so have a more clear understanding of this. So the complaints saying that now the structure has 0 ADP. So we're not supposed to have 0 ADP for all atoms, right? But that's fine. We can directly address that by changing the ADP. So you will want you to use 33. This stands for isotropic ADP. Okay, so that's assuming the disorder, is the same in both directions. We don't have to really care about U1, 2, U1, 3, U2, 3. Those are anisotropic. And unless we have a very high quality data or like the neutron data, otherwise, we do not really, we're not concerned with the anisotropic ADP values. Okay. Okay, now comes to the choice of numbers. So the ADP values here are basically just the UISO values. It's not the B value that we see in Topaz. So in Topaz, a typical B value is somewhere around, does anybody can give me a reasonable guess? What's the typical B value in Topaz? Any guesses? It's actually a very convenient number. It's 1. Okay, so so next time if you come across a structure you're not familiar with, and you need to set some B value in Topaz by yourself, the safest way or the safest number you can start with is 1. So that's a very reasonable and a B value for almost all the atoms. And in general, if the atom is heavy, the number is supposed to be low, right? And if the atom is light, then the number tends to be high, right? But here it's not a B value, and it is the UISO. And that value relates to the B value by the equation UISO equals to B value divided by 8 pi squared. Okay, so those are all mathematics, which comes from they're basically rationalizing the physics. So if you do a little bit searching of UISO B value, I think Google will very quickly tell you how they are related. If you just want to memorize the relationship, so you can memorize as B value is about 70 times, right? So 8 pi squared is about 10. So 8 pi squared is about 80 times. So that's about 80 times or 100 times the value of UISO. So the value that makes sense here is something that is around 0.01, starting from 0.005 to 0.01. Okay, we can start with 0.01. Okay, so in this way we set up the ADP value of UISO for all atoms. Okay. And we can have a quick check. So the number of atoms, they should make sense. We have actually 4 carbons, right? We have 2 methyl on the end, so that's 2 carbon. 1 ethyl in the center, that's another 2, so adds up to 4. So we do have 4 carbon here. So this is 3, there's another one here. So those are the 4 carbons, and we do have 2 oxygens. Right? And also we can verify the number of hydrogens that makes sense. Okay, so now we can actually do a quick run and see if we can directly calculate PDF from this. So what we do is we go to calculations, new calculation, okay, and we're calculating the X-ray PDF data. We just select X-ray and we select a range from 0.1 to 10. That makes a lot of sense because that's probably already big enough for the size of the molecule. And the spacing, which is limited by D4, and scale factor 1.0, that number is kind of random, right? You can change into any number you like, but you do not change the shape of the PDF. Qmax actually influences the detailed PDF pattern because if you have a small Qmax, let's say if our Qmax is only 15, what kind of influence would that have on the PDF pattern? Do we have any thoughts? If we mirror PDF data with a very small Qmax, let's say only 15, what's the consequence on the PDF data we get?
It will smooth out the higher values.
Smooth out? No, it's mostly actually acting on the lower region. So I think we need to explain this more clearly because I think this is important. I think we need to remind ourselves why we need a high energy X-ray for PDF. Why we cannot do PDF at QS, for example. Why we cannot do PDF using lab X-ray.
Because we need long Q range for long range order.
Exactly. No. I was looking for the long Q, large Q, but it doesn't have anything to do with the order. We need a big Q range, right? So that's basically that's the Q max we're looking for. We need a very large Q range such that when we do the Fourier transform, it's a meaningful Fourier transform. Right, because we're basically Fourier transform the data in the Q space to the R space. And if this is a meaningful Fourier transform, we have to access the Q space reasonably large. But if the Q space is small, as in case, for example, in the lab X-ray or in some like long wavelengths inline, the consequence is actually it will produce a lot of Fourier transform ripples. Okay, so when we do the Fourier transform, we'll see a lot of peaks, especially in the lower region, and there's no way to tell whether this is a structure peak or just introduced by the Fourier transform. So we need to do a reasonable Fourier transform. And to do that, we need to access the large Q range. If we do not have a decent Q range, that will generate a lot of fake peaks, basically Fourier transform ripples. Right? And in fact, the same principle also stands behind the Fourier transform exams. Right? So we are all very enthusiastic about getting high K. So, but in exact language, we're talking about K, right? And now we're talking about Q. But they basically have the similar idea. And it's also a reciprocal relationship between the K space and the R space, right? So if you want to have a very good R data absorption, we need to measure the K as long as possible. Because that is the region that will be transformed into the R space data. Okay, so we need to keep being reminded about the principles of these techniques, right? So for Qmax, this is number that we want to set as a reasonably high value. So if we set Qmax as something like, let's say 15, they'll give us a lot of peaks, which doesn't really make sense. And if we set Qmax, we just leave it there as 0, actually the software treated it as a kind of a infinite Qmax. Then you'll see some very beautiful PDF patterns, but which may not match your data very nicely because your data was measured on the basis of a finite Qmax, right? So I'm throwing another quiz. What's the typical Qmax we can get at XPD? 26. Okay, function predicts 26. Any other ideas?
I think we can get up to 50, but we usually cut that off.
50. Okay, Dean is very optimistic. So
40 to 50, right?
Okay. So I guess the young people are generally pretty optimistic. I'm kind of conservative. But 40-50 is really far off. 40-50 is something that you probably can get at the neutron beam with a high resolution neutron diffraction. You have a chance of getting 40-50. But at X-ray, considering the typical size of detector we have, right, and how close we can put the detector to the sample, the typical maximum value is only around 30. 30 is the maximum, but 30 is a super optimal, a super optimistic number. And even 26, in fact, it only appears in some like transition metal oxides. So let's say if we measure NMC, I think you have a good chance of accessing Qmax 26 something, because the scattering is very strong. So you still have the strong scattering even at the edges of the detector. But when we're talking about amorphous components, you're talking about something made of carbon, oxygen, fluorine, even hydrogen. Those are really very weak scattering components. And usually we have to be very careful when we do the masking, right? So if you already have enough experience with PDF, you probably always mask the utmost the frames for the PDF data. If it is a weak scattering sample, I think there's no doubt the most outside frames cannot be used. That said, the typical Qmax for a weak scattering sample or for interface sample is at most 21. So if you go beyond 21, it's very likely some fake signals were introduced into the data. Okay, so 21, I think there is a number that we should keep in mind when we deal with some weak scattering samples. And let's just put 21 here. QDAM. QDAM is something I think we also mentioned in the previous PDF lectures. QDAM, it has the role of dampening the PDF, right? So if we look at the general PDF pattern, we can see that PDF signals kind of oscillates most strongly, maybe around 5 or 6 angstrom region, right? And then gradually you'll see, they're kind of surrounded by an envelope and dampen the overall PDF signal as we go to the higher region. Okay, so that's what the QDAM parameter is doing. And in our standard procedure, we get the QDAM data by fitting the Nico PDF. So what we do is, we should measure the PDF from Nico, which is very nice, right? It looks beautiful. And we should be able to get 26, maybe even beyond for the nickel. And then we can fit the nickel data because nickel structure is super simple. There's no atomic position to fit for nickel. Nickel is FCC. So its position is fixed. So what that means, we can use all the information to fit the other parameters, for example, the QDAM and the QPROD. And these two parameters, they are in general beamline specific, which means, different beamlines usually would lead to different QDAM and different QPROD. And the best practice is to fit a standard nickel PDF and HBM to get those numbers. In my past experience, the QDAM for XPD usually is around 0.03. And the QPROD for XPD is usually around 0.028. It's also close to 0.03. But those numbers may change over time, if there's some upgrading at the beamline. So still, next time if you want to do the fitting by ourselves, we can try fitting the nickel PDF. And I would say it's a very satisfying process, right? You will get a perfect fit for nickel PDF. Okay, so just fill those numbers, and then let's calculate. We go to here, we have everything ready. Okay, let's calculate. And let's see how it looks. Okay, so this is how it looks. There's something kind of weird here, right? So what is weird about this PDF data?
The baseline.
The what?
Baseline.
The baseline?
Yeah.
Why do you think the baseline is weird?
It's going up and down.
That's true, yeah. So the typical baseline should be just a one slope, right? But this one looks like it's kind of a curve, right? I think that relates to the presence of this peak, which is kind of strange.
Oh, that's not real peak.
Yes, this is not real peak, right? For example, if we estimate the size of the DME, let's measure the size of DME. If we just ignore hydrogen atoms for the moment, which makes a lot of sense, from this carbon to this carbon, there's only 6 angstroms. Right? So that's the whole size of the DME. The DME is only around 6.1 angstroms.
So we will need to limit the R range.
Yes, then how come it produces this kind of a long range correlation, which is almost 10 angstrom. This is 9.6 angstrom, right? Doesn't make sense. In fact, also this peak probably is also kind of dubious, right? How come we have this kind of correlation and also this one and this one? I think it makes sense if something just cut off here. So this part is other peaks that are kind of suspicious, right? If we can look at the lower peaks, so for example, this one, 1.14, I guess that stands for the carbon hydrogen, or maybe the oxygen. And there's no oxygen hydrogen, actually. I think that stands for the carbon hydrogen. So let's check carbon hydrogen 1.09. So that's very close. Probably there's a variation. So I think this is likely the carbon hydrogen. And this should be the carbon-carbon and also the carbon-oxygen. That's the strongest peak. So carbon-carbon is 1.5. Carbon-oxygen, that's 1.4. So this peak, belongs to carbon-carbon or carbon-oxygen, right? And this is probably the second correlation. So, we should talk about second or third correlation at some point. I think that deserves a separate lecture, which is very useful tool to analyze the amorphous components. And this is probably another second correlation and third correlation and so on. But peaks over 3 angstrom, this part, they're not supposed to be there. But then why PDFGUI calculates this kind of a peak for us? Remember, the second step in our overall calculation is dummy structure making, right? We need to make a dummy structure to fit into the PDFGUI.
So it's doubling the unit cell itself in this calculation.
What?
So it's doubling the unit cell by unit
Yes,
cell.
exactly. That is what's going on here. So PDFGUI, seriously regard this as a crystal structure and really expands this unit cell in all 3 dimensions, right? And if the unit cell is not big enough, so actually, you also calculate the correlation between different boxes, right? So this 9.6 angstrom peak is actually coming from different DME molecules. Yeah, because PDFGUI regarded as a crystal. Then how do we solve this problem?
I guess the simplest would be to limit the R.
What?
I guess the simplest would be to limit the R.
Yes, that's true. So, that's one way is, if we just want limited R, we simply, we cut off the R here. Okay, we can cut off the R here. But there's a potential challenge. What if, these 2 molecules, they're very close. Actually, some of the peaks in this region also coming from their intermolecule correlation, right? So if they're not fully isolated, there are always a potential issues with this kind of peaks. Yeah. So the solution is simple. We need to make the box big. We need to have big boxes, right? So that, the 2 molecules in different boxes, they are far apart. Let's say they're 20 angstrom or they're, 10 nanometers apart. So there's no way to calculate, there's kind of intermolecule peaks, at least in this reasonable range, right? And the way to do that is do a little bit cheating. That is actually expanding the cell manually. So I'm showing how to do that, okay? So we see here, this is the unit cell dimension we currently have, right? So imagine this is still at the Amazon boxes. This is a cubic Amazon box with the edge over 9.5 angstrom. Okay, and then we put this DME molecule into this 9.5 dimension box. And now we need to expand. The simple way is to double the edges, right? Because now, once the cell is doubled, and the chances are, the 2 cells no longer would have some kind of short range correlations. So we need to increase this number by 2. We also need to make changes to those numbers. Those are the atomic positions, right? Those are the fractional coordinates in the unit cell. We need to change that too. And we do that by copy paste everything Yes, exactly. Excel is one of my favorite. So this is also what I mean by, the spirit of combining all the free softwares and, do something that, that can only be done by paying a big amount of money, right? So. Oops. Yes, something. Copy and paste. Okay, now I have everything here, and make sure that so now, what we should do to the fractional coordinates? Exactly, because now the dimension has increased by 2. If we want to keep the relative position, we need to divide the fractional coordinates by 2, right? So let's do this. Right, equals to this 2, and repeat everything, all the atoms, all the directions. Okay, so these are the numbers, new numbers for the new big box. Okay, let's copy this and we'll this back to and save and paste. Okay, so those are the new fractional coordinates, and don't forget to change this number too. Just lazy and put this number. Okay. This is the cubic, right? Okay. And now let's ask her someone to do the calculation again for us. Now it makes more sense, right? And we can trust PDFGUI that this is a PDF there for DNA molecule. Okay. So I think that's pretty much what we need to know about the tricks and skills to calculate PDF pattern for a small molecule. And when you have time, you can also play around with the other parameters. For example, actually, those kind of delta 1, delta 2, they have some influence on the shape of the relative intensity of the first and second peaks. So for example, if we change this to 0.8, this actually will have some sharpening effect on the first and second peaks. So you can tell it changes, right? But usually we do not get something like that. So there something that makes more sense. And in some cases, maybe we're not even able to get 21, let's say with 19, to also make their piece more broad. And maybe also introduce some ripples, right? And also, the ADP values matter. So for example, this peak is actually the carbon oxygen, right? So if we change the carbon ADP, let's say change in 0.08, something here. So it has some influence on this position. Actually it becomes stronger in a certain way. And also we can manipulate this peak if we realize the merit pattern this peak is very low, then maybe we increase the ADP for this for hydrogen. Then the hydrogen is so weak, so small, so should not have any real change. That's some a little bit different, small changes. So yeah, there's several other things that that we can play around and about the detail, shape, and intent of those peaks. But that's in general how we do the PDF calculation for small molecules, right? And if we want to do PDFGUI for PDF calculation for polymers, we can, first still follow 3 steps. Structure optimization, we need to get a structure, better ending with the PDB, protein database, data bank format, right? So there are several ways. I think ChemDraw can produce the PDB, right? ChemDraw, yeah. So ChemDraw is also one option that we have a ChemDraw. So ChemDraw can also give the PDB data. Sometimes I do a Gaussian calculation, which can also give the PDB file, and then trick the Vector, and also Mercury into producing a crystal structure for us, right? And then feed the PDFGUI with crystal structure, but try to avoid the overlap between different molecules by expanding their cell dimension, and don't forget to change the fraction coordinate for items. Okay, that's pretty much for today. Any questions? No? Okay, then let's just stop here.
Just one, Dr. Hu.
Sorry?
Just one thing I would like to clarify.
One thing you like to what?
Clarify.
Oh yeah, sure, go ahead.
Yeah, the reason why I give 40 as an answer is because I know data can go like 30 something. And of course, when I process them, I cut them off before 20. And that's why I give like close to 40 answer. Like this one is the big.
You mean I think you're talking about 2-seater, right?
No, this one is actually the PDF. When I process through a bit2D.
You think that in future D we can have a Qmax of 40 or?
No, I don't mean the meaningful data is still 40. I mean there's some random data after 20 range.
Random data?
Just not meaningful data. Not this one.
Okay,
like
so
this one.
you can share the screen, I guess, if you want to.
Oh wait, I'm not sharing the screen.
No, because I need to stop sharing first.
Oh, I see. Oh, yeah, like this one.
Yeah, this makes sense, but you see the x-axis is 2-theta, right?
Mm-hmm. Oh, you mean Q range? Sorry. Yeah.
Yeah, what I meant is a Qmax. Yeah, because the 2-theta can vary, right, depending on the wavelengths you choose. But what we really want to use is the Qmax that is going to be directly Fourier transform. Right? We do not Fourier transform the 2-theta.
Yep.
Yeah.
Wait. Yeah, I only remember that 35 number. I forgot the unit. Yeah, that's my bad.
Yeah, and also, by the way, since we talk about 2-theta, I think my experience is usually we want to limit the 2-theta below 35, I think. Yeah, otherwise, well, it really depends, right? You always want to check your data in the high 2-theta region and see if you have some, fishy bumps or some kind of unreasonable glitches that you really want to throw away, even when processing the 2D data, right?
Yeah, this is
mentioned.
why there's a red cross here. I usually cut them off before 20.
Yeah, yeah. So this is what I mentioned previously, that we want to throw the garbage data during the 2D processing. We do not want to bring those garbage data into the PDF get it straight, right? So that when we process, so that will save us a lot of troubles when we process the PDF data. Yeah. Okay, good discussion. Yeah. If there's no more questions, then let's just stop here. Okay. And we'll have no group meetings next week, and yeah, and the week after that, let me see, though that's 21. And we probably will be able to have a group meeting on 21st. Okay. Yeah, we'll see. Okay.